Welcome. So, this is 48H video 1, and we're going to start talking about circular motion. We're going to deal with uniform motion, or UCM. We're going to talk about using Newton's laws with regard to uniform circular motion. We'll talk about 4 classic examples of uniform circular motion, which are more mathematical, and then we'll talk about non-uniform circular motion, the kind of thing where we go in a part of a circle, for example, but we change speeds. This section is very important because it lays the foundation for some mathematics that we actually use a lot in physics 2. And so it's not just that we're interested in uniform circular motion, we're interested in developing some mathematical skills and some ways of describing motion that we're going to use again later. So it's important to get this section squared away. Let's go to the next slide. In this next slide we talk about what uniform circular motion is. And we say a body that moves in a circle has centripetal acceleration. The centripetal acceleration is directed towards the center of the circle, and the centripetal acceleration has a magnitude given by, and it's the centripetal acceleration in meters per second squared is equal to the velocity, if you like, the speed of the object squared over the radius of the circle that the object is moving around. Now for uniform circular motion you have a constant speed, but this equation applies for different speeds in different motions. I can show you that the centripetal acceleration points towards the middle of the circle by reminding you about vector diagrams. Let's imagine this particle just before it reaches 12 o'clock on this diagram. So my velocity initially is up and to the right, and then if I look a little bit later, the velocity is down and to the right, and that's my final velocity. And if I remember that my change in velocity is my final velocity minus my initial velocity, then I can say, well, my change in velocity is going to be my final velocity added to the negative of my initial velocity. Same size, opposite direction. And we see that those two vectors leave a resultant. And this resultant starts from the beginning of the beginning and goes to the end of the end, and so the resultant is pointing vertically downwards. Well, by the symmetry we can see that, oh yeah, that centripetal acceleration points to the middle of the circle. So we have this thing called centripetal acceleration. It's got a magnitude given by the velocity, or if you like, the speed squared over the radius of the circle. And its direction of the centripetal acceleration is always pointing towards the middle of the circle. If we imagine looking down on the motion of an object which is moving in a circle, and we say, well, in uniform circular motion a centripetal acceleration must always point towards the center of the circle. So when the object is here, the centripetal acceleration points there, and when the object is there, the AC points there, and so on. The centripetal acceleration must be provided by a force such as a tension of the string. You don't get centripetal, you need some way of, if you like, paying for this centripetal acceleration. And we know that forces, unbalanced forces, cause accelerations. And so if I have a centripetal acceleration, I must have a force that is paying for it. So at the instant we're showing, I can say, well, my centripetal acceleration is there, and there must be a force in that direction which is paying for that centripetal acceleration, and that would be the tension in the string. That tension might also be doing some other things. If this is a vertical circle, that tension would also be, in some cases, supporting the weight of the object, the pull of gravity on it. And so the tension can do a whole bunch of things. Some people refer to a centripetal force, but I don't like a centripetal force. It's a force that is needed, that already exists or exists independently in your system, and you use part of that force to cause this centripetal acceleration. It's a bit like you don't get holiday money because you go on holiday. If you want to go on holiday, you need to save up. You need to have a job to pay for your holiday. So I don't get circular motion because I have a centripetal force. I need another force to pay for the centripetal acceleration. So I prefer not to talk about centripetal force. It comes in occasionally, but I try not to talk about it. Interesting point. If the string is broken, the centripetal acceleration is lost and the object is no longer constrained to move in a circle. So if I break the string, then what will happen? The object is in equilibrium and thus will continue in a straight line. Remember, this object wants to travel in a straight line obeying Newton's laws. And the thing that's stopping it from doing that is this constant acceleration which is causing it to change direction. If it wasn't for the centripetal acceleration, the object would travel forever in a straight line at a constant speed. Given the situation's geometry, the straight line is a tangent to the previous path. So if you were to break your string, you would travel in a straight line. Let's try a few questions. What is the centripetal acceleration experienced by a 5 kilogram mass that moves at 12 meters per second around a circle that has a radius of 4 meters? Imagine looking down from above, and we have our 5 kilograms, and it's moving in a circle, and that radius is 4 meters, and the velocity is 12 meters per second. So what do I know? I know my mass is equal to 5 kilograms. I know my velocity is equal to 12 meters per second. I know my radius is equal to 4 meters, and I want to find my AC. So I'm going to put on my thinking cap and I say, well, oh yeah, AC is equal to V squared over R. So AC is equal to 12 squared over 4. AC is equal to 144 over 4, which equals 36, and that will be 3 goes into 14, 4 goes into 14, 3 times carry 2, 4 goes into 24, 6 times meters per second squared. So there's my answer. Oh, hold on, we didn't use the mass. Yeah, the mass is not involved in the centripetal acceleration. So just because I give you the mass doesn't mean to say you're going to use the mass. Then the second bit, if the string that holds the revolving mass is cut at an instant shown, which path will the mass take? Most common misconception is that the object will simply move away from the circle radially. If people start thinking about air drag, sometimes they'll draw the second most common misconception, where they have some kind of curve taking place. But the fact of the matter is that the correct answer is that as soon as the tension is released, then you have an object which is simply in equilibrium, and it travels in a straight line at a constant speed unless some other force acts on it. And so as far as we can see, it's going to travel in a tangential direction. Nice conceptual question. So there we have it. Next time we'll look at some more involved calculations. Thank you.